Hi everyone, today we're going to learn about buffers and titrations, and then next time we're going to do I need to think straight, a little bit of KSP and KF. All right, so we all know about the dangers of antifreeze, and we really shouldn't drink it, although it does have some interesting effects, like it's sweet and it could make you feel like you're drunk. However, high enough concentrations, it overwhelms our buffering capacity that we have in our blood, which is not good. We do need our pH to stay at a very specific range in our blood, and this glycolic acid or antifreeze throws that off, which is bad. Also, why would you want to drink antifreeze? But I'm sure maybe it's available for minors, things like that, and so they can get the effect of being drunk. Okay, so we are very happy that our blood has a buffer solution. You will need to know what a buffer solution is and what affects it. So buffer solutions are solutions that resist change in pH when an acid or a base is added. And then also buffer solutions must either contain a weak acid and its conjugate base, or a weak base and its conjugate acid. So notice there are no strong acids or bases in buffers, only weak ones. Also, make sure you know that the conjugate is the one that goes with it. Okay, so to make a buffer, again, you're going to need a weak acid and its conjugate, or a weak base and its conjugate, and it must have significant amounts of both the weak acid and the conjugate. Okay, so when this happens and we have a good buffer solution, if you add a base, it'll be neutralized by the acid. And if you add an acid, it will be neutralized by the base. And so then the pH stays the same or changes very little. Okay, so with Le Chatelier, how they work, because we're going to tie back into Le Chatelier. If I add base to my solution, so I add some OH, the HA will counteract it to make more water. Okay. If I add acid, the A- will combine to make HA, and so my concentration stays about the same. Okay, common ions, we are going to start seeing common ions. This is when we add a salt. So here the example is we're adding in sodium and then A, which is an anion. And when I add that in, it's going to count as this piece, just that piece. Okay, because sodium's a spectator ion. Spectator ions are the ones that cancel out. They're not really affecting our reaction. Okay, so once I add that in, it shifts my equilibrium sum. Okay. All right, so we need to calculate our buffer solution using an ICE table, okay? The second way is easier, but we're going to do this way first. Okay, so I've got HC2H3O2, and let's go with water. I don't know. Is C2H3O2 minus plus H3O plus. Yeah, okay, so that's the equation they wanted. We do our ICE table. Now I have 0.1 molar to start here. Remember, water doesn't count, it's a liquid. But I also have this anion in there of 0.100. Okay, I have nothing here. This side is still plus X. All right, so I've got 0.1 minus X, 0.1 plus X, and then I've got X. Okay, acetic acid, so we've got our Ka is 1.8 times 10 to the negative 5 is equal to our 0.1 plus X times X divided by 0.1 minus X. Okay, remember we can count our plus and minus x as negligible. And then if you look at this, the 0.1s will also cancel out. So x is 1.8 times 10 to the negative 5. And then if we were to find the pH, I get 4.74. And there's our answer at the bottom, 4.74. Okay, remember, plus x and minus x are so small, we cancel them out. That way we don't have to do our quadratic equation. All right, so let's do a little bit different one. Now it's changing. So we've got our same equation, C2H3O2 plus water yields C2H3O2 minus plus H3O plus. I've got 0.2 of this now. Don't care about water. I've got 0.1 of my sodium hydroxide, and I've got 0. So plus x minus x, 0.2 minus x, 0.1 plus x, and then x. Again, our Ka is still 1.8 times 10 to the negative 5, but now it's equal to 0.1 plus x times x over 0.2 minus x. Okay, so remember, our x's plus and minus disappear. And for this, I get x is 3.6 times 10 to the negative 5. Remember, that's molarity. pH is the negative log of that, 4.44. Okay, so it changed a little bit, and that's because I had a different amount of acetic acid. Okay, so they're doing the same thing on this next one, but it gives you formic acid and sodium formate, and I don't know off the top of my head their K values. But it's the same process. Okay. All right, there is an easier way to do this. However, the ICE table always works. So this is a much easier method, and you are welcome to use it because it'll work for us. But the ICE table will even work in more difficult situations. Okay, so this is called the Henderson-Hasselbalch equation. It's the pH. You find it from the pKa plus the log of the base over acid. Okay. So this is just how it's derived. Gets you that whole thing. Remember, it's base over acid. Okay, again, the ICE table always works. Henderson-Hasselbalch works when we use the approximation method, which is what we're doing. So it'll always work for us in this class. Okay, so here they gave us Ka. Remember, our equation is pH is equal to pKa plus log of base over acid. Okay, so our pKa, we just take the negative log of our Ka, and I get 4.19 plus our log of base is sodium benzoate, 0.150. And then on the bottom is our benzoic acid. So this happens to be the log of 3. And I get that the pH is 4.66 total. And there's their answer, 4.66. Okay, notice they are showing you can do it through the equilibrium approach as well. Okay, but note we can use the Henderson-Hasselbalch for this class all the time, which is much easier. Okay, so here's another one. I'm going to do this one up here. So pH equals our pKa. Look, they gave us our pKa, 9.31. How nice of them. Plus our log of our base, which is KCN. So 0.17 over 0.25. So 9.31 plus log. You will need to put this in parentheses, the 0.17 divided by the 0.25. And I get 9.31 0.14. Okay, so it is super easy once you know what's going on with the Henderson-Hasselbalch equation. All right, so now we're going to talk about when we add acid or base to that buffer solution. So that was just calculating buffer. Okay, and remember, it shifts, so it reestablishes that equilibrium so the buffer stays the same. Okay, so the pH should remain relatively the same, or it should change very slightly. Now, it should not change more than 1 pH. If it changes more than 1, it wasn't a good buffer. Okay, so how do we calculate it when we add an acid or a base? So there's the stoichiometry, and then there's the equilibrium calculation with new values. All right, I'm going to walk through this one with you. I'll do the next one, okay? So notice we've got moles this time instead of molarity, but look, it's 1 liter. Okay, it gave us Ka, and it gave us pKa. Okay, so it wants us to calculate the pH after we add 0.1 moles of sodium hydroxide, which is a strong base, to our equation. Okay, and notice it's still 1 liter. All right, so now we need to work in moles. Okay, we're adding base to our acid. And so see, we start with 0 base. I add in 0.01, sorry. And then I subtract that amount from the acid because I use the acid to neutralize that. And then it makes the anion on the other side. Okay, once we have those values, we do a new ICE table, but remember X is irrelevant, so they cancel out. Okay, and then we plug in, we can find pH. Great. You can also do it with the Henderson-Hasselbalch, but you have to use, remember, these are the new values. New molarity after base is, I'm going to put adjusted for base. Okay, so now it wants us to calculate it for the solution, the same solution, but now we're going to add 0.015 molar. So it told us 4.74 was the pKa. Let's just double check. Sorry, it's a lot. Yes, 4.74. I've got 0.1 molar of my initial pieces. Okay, so 0.1 molar C2H3O2 and C2H3O2 minus. Okay, so we're still adding our base in. All right, so our base started out with nothing. I started out with 0.1. 0.1, I added in, so this is 0.015. I need to subtract it from here because it's losing that much, sorry, 0.015. And then it gets added on the other side. Okay, so once this is used up, it's gone. This goes down to 0.085, and here we're at 0.115. Okay, so the whole goal of this piece is to get used up by your acid. Once you have that, we can plug these values into our Henderson-Hasselbalch equation. So I've got 4.74 plus the log of our base over our acid, so 0.115 versus 0.085. and I get 4.87. So notice before I had 4.83, I added 0.005 more moles of sodium hydroxide, and it brought my pH up some. Just remember, if you're adding base, your pH should be coming up. And if you're adding acid, it should be coming down. Okay, there is one with the I wish I could erase this better. Oh, maybe I can. Okay, I could erase it all. Okay, so we've still got our pKa is at 4.74. I still have H2 or HC2H3O2 and C2H3O2 minus both have 0.1 molar. Ooh. All right, so now we're starting with HCl. So our HCl is a strong acid plus that makes HC2H3O2, not minus. Okay, so I've got none. I'm adding in I've got 10 milliliters of a 1 molar acid. So we do have to find the moles of that. So 0.01. Okay, so this is 0.01 because it was, remember, molarity is moles per liter. So to find moles, you do molarity times liters. Okay, and then this was 0.1, this was 0.1. I'm subtracting it from here, and I'm adding it to the other side. So this comes out to 0.09 and 0.11. Okay, now our base is the other one. So our pH is 4.74 plus log of base is 0.09 over 0.11. And I get pH is equal to 4.65, which is the direction we should be going in the event that we're looking at adding an acid. Okay. Now I do want you to know I may only ask one question on this on the test. Okay, so don't freak out if you don't get this, it'll be all right. And there's no quiz over chapter 17. All right, so buffers can also be a base in its conjugate acid. So we've kind of been using the acid in its conjugate base, but it could go the other way as well. Again, they need to be as close to equal proportions as possible. And you can find the pH the same way. pKa is equal to log of base over acid. Okay, but remember this equation with our Ka and our Kb and Kw? So pKa and pKb are also equal to 14. So you could find POH from this equation. pKb is equal to log of acid over base. It doesn't matter to me which one you use, but once you find POH, you then have to find pH. Okay, so this one gave me the pKb, and it gave us our base and our acid. So remember, it's POH, is equal to pKb plus log of, this one is acid over base. So I've got POH 4.75 plus log 0.2 over 0.5. I get 4.35, but remember that's POH. So our pH is 9.65. Okay, so just make sure you know which one you're doing and what pieces you have. Okay, so for this, we're doing the same process that we were doing before. Now we're adding some base in there. So I've got our OH is with our NH4 plus, and that's going to make our NH3 plus water. Okay. I've got no base to start with. I've got 0.2 and I've got 0.5. Okay, water doesn't matter. So then remember, we're assuming it's in a 1 molar or 1 liter solution, which here it says it is. So then we've got 0.01 moles. I'm going to subtract that from the side I just added it because it's going to cancel out. I'm going to add it to the other side. So I've got 0.19 and I've got 0.51. Okay, so we do our POH equals 4.75 plus log acid is 0.19 over base 0.51. Okay, and I get pH is 9.68. Okay, I did add base. It is going up. The original one was 9.65. It went up slightly, not very much, but it went up some. Okay. All right, your buffering range is the pH range where your buffer is effective. And again, that's plus or minus 1 of the pKa or B. That's what it's going to be. Your buffering capacity is the amount of acid or base your buffer can neutralize. And the effectiveness of your buffer is related to the amount of acid and base, but also the concentration of your acid and conjugate base. All right, so here's our Henderson-Hasselbalch. Again, our effective range is within plus or minus 1 of your pKa. Okay, a buffer is most effective when the concentrations are equal of your acid and base. Okay, also it's most effective when you've got large amounts of acid and base. I know those aren't red, but those are important. Okay, so here we're talking about buffering capacity. Notice if we have a very concentrated buffer, like the picture on the left, it's easier for that to combat a acid coming in than it would be for the diluted buffer because it doesn't have as much of it. Okay, so buffering capacity specifically is the amount of acid or base that can be added without causing that large amount of change. And if you increase the concentration, you increase the buffer capacity. Okay, if you need to make a buffer that works mainly with acid being added, you need more base than acid. And if you're working with one that needs to add base, you need more acid than base. This is in a real world situation, or when we were in a real lab situation, we may do something like this where you get to choose how to make the buffer, but we cannot do that with at-home labs. All right, so we're preparing a buffer. Which acid would you choose to combine with your salt if you want your buffer capacity to be 4.25? So remember, we want plus or minus 1 from this. So that gets rid of chlorous acid, but also hypochlorous acid. So we're looking at those two. I'm going to say the best one is going to be our formic acid, and that's because it's the closest. Okay, in what example would we want the pH to be 7.35? Okay, so for 7.35, we would be looking for hypochlorous acid. So it's just a matter of what we're looking for. All right, now we're going to shift gears a little bit and go to titrations. So for titrations, and you're going to do a simulation at the end of this week, actually week 3. And what happens with this is you've got an unknown concentration or your titrant that's being added to your solution of a known concentration, which is from your burette. Okay, the equivalence point, this is super important. Hopefully you talked about it in chapter 8 in Chem 1, but if not, it's okay. So the equivalence point is where your moles of acid are equal to your moles of base. And an indicator is normally how we visually see it. So indicators change color with pH. And so when that happens, you can see that our pH changed enough. However, the end point is when the pH changes the color of it. Okay, so sometimes we use pH meters, and sometimes we use indicators, and sometimes we do both. But the end point shows us where the color changes, and that's where we say we want it to be close to the equivalence point. Okay, so here's an example of a titration. So here we're starting from clear, and this is what the simulation, I hope, has. Clear to pink is what we want to do just because it's the easiest to see for people that are colorblind. And once we've added enough base, it turns that pink color. And it needs to be pink throughout, not where it swirls out. Okay, you're going to be encountering a lot of these titration curves, and these are very important. Just know that if we're doing a strong acid, strong base, your pH should be 7 at equivalence point because that's where it's neutral. All right. Also notice this whole region where this S curve is, this is a very steep slope. And when you're doing a titration in the lab, if you're not paying attention, you're going to miss that whole thing. And you're going to go from clear to pink and it's done. And most of the time in lab, we do 3 trials just to make sure you're right and that everything is good with that. Okay, so there are steps for this and I will post them. Okay, I will need you to be able to calculate strong acid, strong base. Okay, so we need the pH at the equivalence point. So notice this says sodium hydroxide, nitric acid. Those are both strong. The equivalence point, pH should be 7. The first thing you should always do is find the equivalence point, which is with the dilution equation. So for this situation, I've got 50 mils times 0.2, and I'm going to divide that by 0.2, and how convenient. So equivalence point is at 50 milliliters of HNO3. Okay, that's the first step because you need to know where you're at on the equivalence point. Okay, you also need a starting moles of your titrant, and that is going to be our 0.050, so starting moles. So I've got 0.05 liters times 0.2 molar, and this is of our base, so 0.05 times 0.2. I've got that's a big decimal, 0.01 moles of our hydroxide. And from that, I also need to know how many moles of our acid I have. So I have 0.03 liters of our 0.2 molar acid. And I have 0.006 moles of H plus added. Okay, so this is kind of like that buffer where we were talking about the acid and the base. So what we're going to do is we're going to subtract these two. And my acid's going to get used up completely. And I'm going to have 0.004 moles of hydroxide left. Once we do that, we need to then find its molarity. Okay, so now I've added 80 milliliters, so 0.08 liters of liquid is in my solution. Okay, that gives me a 0.05 molar hydroxide solution, I can take the negative log. My pOH is 1.3. So my pH is 12.7. Okay. So they went through the whole process, same thing, 12.7. pH at equivalent should always be 7 in a strong acid, strong base situation. Okay, so now we're going to add 60 mils of our HNO3. So remember we had 0.05 moles of our, is that right? And of course, this is a calculator that can't go up. No, 0.01 moles, sorry, of our hydroxide because that doesn't change. Okay, that's how much we started with. For our acid, we now have 0.012 moles of acid. So now our base is the one that's getting used up. So we're subtracting them still. The bigger number is the one that comes out on top. So 0.002 moles of acid is what's left. Okay, we still need to divide that by the total volume, which is 0.11 liters. And I get 0.109 molar. Remember, that's of our acid, so now we can just take the negative log of that. And I've got my pH is 0.96. That's super small in comparison, y'all, to when I added 30 milliliters of the acid, and I was at 12.7. Okay, so it goes very quickly just because of that S curve on the titration curve. All right, for weak acids and strong bases, I'm just going to need you to be able to identify on one of these titration curves the parts. So first off, notice the pH is greater than 7 at equivalence. Okay, so you need to know that. Also, these flat regions are going to be called buffer ranges. Also, pH starts higher. Okay, you're going to have to do a whole lot more for these, so I'm not going to ask you to calculate a weak acid and strong base or a strong acid and a weak base. Just notice the parts of the titration curve because you could be asked that. Okay, so it's walking through what to do. Again, you're not going to have to calculate this. As you can see, it's much more involved. So all you'll have to be able to do on the ones that are not strong, are identify the parts. So here we've got our strong base. This one's the new one. Notice pH less than 7 because it's got that strong acid. The lower pH here. Okay. So, and this is still that buffering range, okay? Okay, if you've got a polyprotic acid, notice there are 2 equivalence points. And again, I'm not going to ask you to calculate any polyprotic acids, but you are going to be able to need to recognize them based on their graphs. All right, and in lab, we would normally be monitoring with a pH electrode, and this gives us readings at every point, and so then we see how much the pH changes over the addition of our titrant. Okay, remember indicators are more used when you need a rough estimate, not a graph. So an indicator, remember, changes colors at the end point, and it needs to be very close to that equivalence point. Okay, so here are our indicators shown in colors on our graph. Notice we're at clear, clear. We're turning a light pink. That's the in-between. Once you're past that point, though, you're gone. Okay, and indicators are weak acids, so just be aware of that. Not enough to matter, because remember, when we have a strong acid and a weak acid, the strong one is the one that matters. Okay, so here's just some indicators. We almost always use phenolphthalein, again, because of the color blindness. It's the easiest to see. The methyl red is not as easy to see if you're colorblind or have some degree of color blindness, because that middle number, that orangey, is kind of hard to read. Okay, and here's a whole table of indicators. Sometimes at the high school, when I'm doing titration curves, we try to pick different indicators, my students do, and then and occasionally I don't have like phenolphthalein, or I don't have enough of it, especially my biology department loves to use phenolphthalein for their virus simulation, but really they could be using any of these indicators as long as they change around the same time pH-wise. So, all right, and that is it for the day. I hope you'll have a good day.